Actually, for monsoon, we have long rain, but finally it was clear from yesterday since you came here, everybody from China. Okay, the saying Murphy's law is American proverb, kind of new proverb. Every time you want to do something important, some problem happens. Okay, so we have some problem with the internet, I guess. Okay, today is the 27th. This is typo. Okay, the material I'm going to talk about is some new finite element scheme to solve the problems with the interface. Okay, when we have an elliptic problem and the problem has some material interface, then PD has some interface condition, right? So we start with some introduction and some basic finite element based on P1 polynomial, and then we give some analysis for that, and we introduce the new P1 FEM. And then to motivate the new, we introduced. The DG, the known technique DG, and we using the DG we modify the given FEM. Then we proceed with H1 and L2 error estimate, and finally a numerical experiment. There are many physical phenomena arising from the nature or engineering has a interface, right? And okay, let's go to this way. The examples of interface problems are abundant from almost everywhere. Okay, so most common or important application area comes from petroleum engineering. Modern numerical analysis is quite related to petroleum engineering and flow. The media underground mostly has a lot of interface and different materials and rocks and soils and sands and things like that. And the modern technology has used composite material, to manufacture some new device. Okay, and also in fluid mechanics, we have a classical two-phase flow: oil and water, oil and air, etc. Water and air, etc. And recently, we have some application to cell biology. Especially a cancer cell has a quite different conductivity, or maybe if they use some electric device, permittivity and things like that. And cancer cell has different material properties, and etc., etc. And especially for time-dependent problem, the interface may change. Then we have quite a difficulty to adjust the interface. Okay. So we start with a simple model problem, elliptic type equation. And the beta is usually the diffusion coefficient, for example, if it is heat equation. And the natural condition, naturally, or physically, this bracket usually means the jump across the interface. The interface looks like that. This is the interface. This is the interface. Oops. Okay. And this bracket means the jump across this interface, we denoted by gamma. Okay, I have the domain here. Where is the domain? I forgot. Okay, this is the domain. Yeah, domain. Okay, inside is omega minus, outside omega plus. The interface denoted by gamma. Okay, so and naturally, this is a flux condition, a natural flux condition. And for simplicity, we assume beta is constant, for piecewise constant. So beta is discontinuous across gamma. And then the two kind of grid. To solve this numerically, say finite element method, usually we have to use a fitted grid. This circle is an interface, so we roughly resolve it by triangulation. This is the traditional method, and almost everybody, 99%, 99 people use this fitted grid. Nobody uses this grid. Okay, this is a uniform grid, ignoring the interface. And then around the 1960s or something, people noticed that this does not work. They tried, of course. They tried. This is simpler, you know. This grid is simpler, so they tried it. But when the coefficients are discontinuous, this grid does not give optimal error. They deteriorate a lot. You know? But the reason, okay, if we look at try to see what's going on, why it fails, okay? Let's see the one-dimensional example. It's just a simple one-dimensional example with a certain boundary condition. Then for this case, we have exact solution. Okay, kappa is 1 on half of the interval and 1 over beta for the other half. Then with this certain, we have an exact solution. Okay, this exact solution is continuous. Okay, and satisfies. Okay. Satisfies this normal flux condition at the midpoint is 0. So this is the exact solution. Okay, this is the exact solution, and the interface is located at the midpoint, 1/2. Okay, but if you use a grid, finite element, so you just you make the grid, and grid resolution does not is match the interface. Then in the finite element method, we use a P1 basis function, linear function. So connecting linear function connecting this point and this one. So it's red color, you know, red color. So, and then we see evidently the error is here. Maximum error is depending on beta times or whatever. Okay, maximum error is error is over h. H is the size of this grid. Okay, and ideally we are expecting of h square. So from the interpolation point, we already see that we lose 1h. That's why we lose the optimal error. Okay, so nobody uses this one. But about 10 years ago, a group of actually American Chinese people tried to use the uniform grid instead modifying basis function. Okay, so by seeing this, we can say, what if we can somehow modify this? You know, modify. So we use not P1, just as a broken P1, a kind of sense. Okay, and it seemed to work. Okay, but two-dimensional, one-dimensional is trivial. Two-dimensional is not so trivial. And anyway, they tried it, and they tried some examples. Okay? And they claim it works. And okay, now some properties of interface solution. Let's try. So for interface problem, we have globally H1. Okay. But locally H2, on each subdomain H2, globally only H1. But for good elliptic problem, we have H2, right? Or H1 plus alpha, but this one has only H1. So we use a fitted grid, but if you use fitted grid, then it costly more and it's expensive to solve, especially for time-dependent problem. So this is the people who initially started to use a uniform grid for problem with the interface. Okay, so he's in North Carolina State. He's in Hong Kong now. He's in Canada now, in Hong Kong and Virginia Polytech, etc. Okay. Okay. So the usual. You can start with the usual finite element variational formulation and with some broken norms, and this is the irregularity result is known. Okay, irregularity is known, and for okay, now let's see the original, I mean the 10 years, the original, we call it IFEM, oops, sorry, IFE immersed finite element method. Okay, use grid or a uniform grid or any shape regular or maybe quasi uniform at least, okay? And it ignores the interface, so interface can cut through the element, okay? And the idea is to modify the shape function, the basis function, to satisfy the flux jump condition, okay? In some sense, you know. So we see for standard this notation, T is of course an element, and the T star HB is a collection of interface elements. Interface means an element that cross with interface. Then as the notation with bar means it is flat. Bar means I use bar for meaning for flat, okay? Standard basis linear shape function. But for that with interpolation error is well known. And then we use the, this is the typical interface element. And then there's the smooth interface is here, but we can approximate by a piece of line, so it's okay. And then, of course, for analysis, we need some subtle, we need to treat the subtle inconsistency here. Anyway, there are a few cases we want to avoid. So assumption on the grid is this one. We do not want more than 2 points of interface point passing through one element, okay? So we do not want 1, 2, 3, 4, okay, like this. And also we do not want for each edge, we do not want two cross point, only one cross point. This is a typical case. Each edge can cross, I mean the interface can cross each edge only once, not twice, okay? So these are all problems, and we don't want this cusp happen, okay? But these can be mostly avoided by refining the grid, okay? So as long as the smooth is, the curve is smooth, not C1 smooth is enough, okay? So, so see, go to here. The idea is to impose this condition. We use two piecewise linear functions, okay, on this, okay, here. Usually we have 1, 2, 3 unknowns, and the usual basis function is just linear here. But instead of that, we use two pieces. One linear function, another linear function. But they have to be continuous, so we need a continuity along the line, right? Actually, continue at the 2 point. And another continuity is the flux derivative. So we impose those three conditions. Actually, continuity and flux. Then together with the basis, nodal basis condition, we have six equations in 6 unknowns. And this has a unique solution. So that is the original idea for using Lagrange basis. So when I say Lagrange basis, means it's 1 and 0, 0. Okay, it's a standard notation, right? But that is original. Original. I say two type. Why is two type? Original basis is a Lagrange type. Okay. So it's vertex value. The vertex value is 1 or 0 or whatever, okay? And we usually people call it conforming P1 FEM. It's meaning it's continuous, okay? But here we use a slightly different name because conforming, non-conforming usually understand as one is a Lagrange basis, another is a Crouzet-Rabial non-conforming type. So that means that this is based, the DOF is, degree of freedom is located at the edge, at the edge. Degree of freedom is, where is that? Okay. Degree of freedom is not at the vertex, but along the edge, okay? Usually people take the average value along the edge. For linear function, the average value along the edge is the same as the midpoint value. So they do not distinguish. But for this particular application, we have to use the average value. The point value, midpoint value does not work, okay? That's one thing I want to note. But anyway, there are two types. Okay? One is the Lagrange type, another is, well, I may call Creux-Rabier. It's a little bit long, but some people say this is conforming, this is non-conforming. But actually, if we use modify, break it, you know, so they satisfy the flux condition, both of them become non-conforming. So there is confusion in the world. Both of them are non-conforming. So usually people mean non-conforming means the second type. Eh? So whenever I write something and then the referee just get confused and they complain about this. Okay? So I try to call one Lagrange type, another is Creux-Rabier type. Eh? But I keep on saying conforming, non-conforming. Eh? Okay. So what is the advantage and disadvantage? Okay. So this is the first one suggested by those people. Lagrange type is more popular. Almost every engineer uses vortex valued DOF. Okay, it's well known. It's undergraduate. Everybody wants to. Okay, either this or maybe triangularized like this. Okay? Like this. So they try to assign unknowns at the node. That's no. Somehow people like to use this. It seems to be easy to understand, or maybe easy to implement also. And more than 90% of codes are written based on vortex point. Okay, and the Lagrange type has less degree of freedom compared to edge degree of freedom. Edge, okay, degree of freedom lies here. Okay, lies here. So it's the number of unknowns, vortex versus edge is about 1/3, 1 to 3. So it's about 1/3 less. So why use Creux-Rabier element? It's more complicated, right? But we need to use it to solve Stokes equation, or maybe to solve elliptic equation in mixed form. This Creux-Rabier type is necessary. So this is also a very useful element. But disadvantage is, of course, CR. CR is that it has more degree of freedom. But for this application, for this IFEM, originally the people in America started with Lagrange basis. Then they did not have the proof, complete proof. They have some numerical results, and I believed it. And I tried to extend it to a non-conforming or a Creux-Rabier type. And there was in early years there was maybe some miscommunication, and people thought this Lagrange type was working quite well. And not so many people tried examples, or just a group of people tried a few examples. And then later on, okay, I tried. Actually, my student did computation, and he said it's not always good. It's good for some problem, but not so good for some other problem. So he was not sure also. I was not sure. Later on, after we tried the Creux-Rabier element method, and then we saw that this is perfect. This works. Every problem we work. Of course, the proof. Okay, we have proof for both, but turns out that proof for this version was clear, but proof for the original Lagrange type was very complicated, very difficult to prove. So, recently I'm not sure whether the proof is correct or not. But there are some examples that numerical examples. There are some deteriorating cases. Okay, so one of the purpose of this presentation is to modify the original IFEM. Okay? So my introduction was rather long. Modify the original. Okay, let's skip some details here. Just all function spaces and conditions. this approximation property was, of course, proved for both of them. Actually, this proof works for both Lagrange type and Crowell-Rivera type with slight modification, but quite technically quite difficult. Okay, so let's skip. Instead, we have to use a lot of function spaces depending on each piece regions, and also there are 4 terms in, for example, in defining the semi H2 norm. The reason is that original domain, okay. This curve, we try to include the smooth curve case. Smooth, I mean, most of the interface is smooth, and this is approximated by the line, okay. And then we may say just, okay, this is a variational crime. We may replace it without losing any optimality, but it's not clear, right, in this case. So I have to include the 1, 2, 3, 4 domains, and then they give detailed analysis for the interpolation errors. But anyway, this is quite technical, so let's skip this, and then we'll see the result only. So this is ordinary interpolation error, which is optimal. And then, okay, this is the original IFM, and the Poincare inequality is not a big problem. Okay, now we are going to present our originally modified IFM. You know, IFM is already modified from standard one. I modified it once more. Anyway, I call it modified IFM by the idea of discontinuous galerkin method. Okay? The problem of original, the first IFM seems to come from the inconsistency. Okay, something like that. Okay, this is a typical 2-element, and this is the interface. Then the function, the basis function is broken here. So there is this discontinuity here. Discontinuity arises. Even the original P1 function is continuous along the edge, but this after broken, broken this way is discontinuous. And then we have a so-called consistency error. Okay? Consistency error. This consistency error is supposed to be optimal. So it has to be O of H, but eventually it seems to be we are losing something here. So to resolve this problem, I used the discontinuous galerkin method. The idea from there. Okay. So for that, I briefly describe what is discontinuous galerkin. This is completely, in a sense, completely different finite element method, but we'll combine it. Okay. Originally suggested by Douglas, Dupont, whatever, Wheeler or Arnold, all famous guys. And then the simple idea, we do not consider the interface problem, just the standard domain partitioned by any grid. Okay. But they use a completely discontinuous basis function. Okay, no degree of freedom are connected by each other. Okay, instead they use a line integral along the edges to kind of as a kind of penalty. Okay, and then they can use no matching grid. They can use any kind of grid. Okay, they can use all any degree of freedom polynomial. For example, you can use degree polynomial P2 here, P1 here, P3 there, everyone. It's very free. Instead of this disadvantage is the many more degrees of freedom. Okay? Because this continuum, each triangle has 1, 2, 3 DOF, and this one has also 1, 2, 3, 1, 2, 3. So along the vertex, we have actually 6 degrees of freedom. It's huge actually, but it has this advantage also, many advantages. Okay. Okay, so to derive discontinuous galerkin method, we go back to original PDE and the integration by part, but because of discontinuity, our line integral term is always alive there. Okay, so to treat that, after we integrate on each triangle, integrate by part and sum it, then we have a lot of this line integral term coming from each. Okay, and then we treat this line integral using this small identity, small arithmetic, and change it to this form, this way. This brace means average, and this bracket means a jump between the two. So using the average and jump and average and jump the other way. This is if U is the original solution and V is piecewise any polynomial, piecewise polynomial. Then from this is the motivation of DG, and from this they a lot of people there derived a new scheme. Okay, there are several various discontinuous galerkin depending on some term that doesn't hurt the original form. Instead the basis function is all discontinuous. To compensate for that, they have to add this line integral term, okay? The jump term between the edges, okay? The jump term, they control the jump term, and there is some parameter depending on the coefficient. Otherwise, it does not work. Okay? So anyway, it looks quite complicated. Anyway, okay. Now I want to combine this into my original, not my original, their original IFM. Okay? So okay. And propose new, call it modified P1F. Names are a little confusing. Okay? So okay, look at the general form AUV equal FV. That's very typical. This is a typical term, gradient U grad V. When modified by two terms. Okay? One term is B epsilon, looks like that, and another term is J. J means jump. So if you look at these two terms plus this one, compare with the DG case, it's exactly the same. This term, and this term. Okay? This is B, this is J. Okay? Looks exactly the same, but there is difference. Okay? What is the difference? In DG, we use completely discontinuous basis function, okay? And we have a lot of DOF. Okay? Maybe about six times as original. But in our case, we use a P1 continuous function, P1 basis function. It's only one DOF here. The difference is that we still use the line integral, but these line integrals are only actually mathematics on the presentation. It looks the same, but number of terms here, are much less. Okay? Much less. So this final form. Okay. A epsilon U modified whatever, this is FEM form. This falls into ordinary standard finite element type. Okay? The matrix falls into the same unknowns, same matrix structure. Okay? Almost same, I guess. Okay? And then to estimate, we need to introduce now a more complicated line integral terms along the edge, and also U jump, function jumps, etc. But using some technique coming from DG, discontinuous galerkin form, and inverse inequality, and then the trace inequality always. It's all technical, but if I can, I have to. I don't have to measure all this, right? It's just kind of standard, Poincare inequality and coerciveness, etc., etc. So the difficulty, is a technical difficulties, not really difficulty, conceptually not so difficult. We have to bound all these line integrals by standard H1 norm and the jump condition. Just okay. Using that, we have to show. What is that? We have to show this A form is coercive. It's greater than this triple norm is almost like H1 norm, but this is bigger than H1 norm. Okay? So anyway, the full norm used in here is a triple norm. Okay? The triple norm is actually one norm. Okay, this is this is L2 norm, one norm plus the line integrals. Okay, so after we provide all these technicalities, okay, then final proof is very simple. Yeah, okay, okay. So let's go back to the go to the example then. So we have many examples. I provide many examples, okay, with the exact solution with discontinuity along this. I even tried the one with some cusp inside. Okay, so this is a graph. Okay, and okay, let's look at first two column. Okay, first two column. We compare for that problem original IFM and the modified one. If you look at order, the original order is 2. 2 is the optimal case, but it seems to suddenly decrease for certain cases. But our new case stays as 2. Okay, one norm also the same. This is almost 1 optimal. This is less than optimal, and depending on some problem is also good. Okay, both of them are good. Okay? Sharp corner, inside is sharp corner, and then we again, okay. For this problem, IFM seems to be almost okay, okay? Almost, but this one is, our is slightly better. And finally, what is that? With different kind of, different kind end, corner with different angle, okay? Again, the original IFM goes down to 1 while we stay at 2. So, I hope my second modified one is useful. Thank you.